Hey, John here. Let's look at these RISC-V pseudo operations or pseudo instructions. All right, now I kind of copied this out of the version 2 of the instruction set manual for RISC-V. You can find a link to that in the bibliography of this document. Remember, this is my RVLP document. You can get this thing on GitHub at this link right here, github.com/johnwinan/RVLP. I'll put a link to it below in the notes on this video. So what are these pseudo operations? Well, it turns out there are very common sets of instructions, one of which we want to use in some assembler code that we're going to write to start up a C program, and it's going to be called load immediate. Now, if you think about the instructions, we're already familiar with the 40 or so instructions that RV32I can execute. There is no instruction in there that will let you just load a 32-bit value into a register. So if you want to load a 32-bit value into a register, one way to do it is use a LUI followed by an add immediate. Okay, remember the LUI takes a 5-digit hex number and stores it into the left half of the RD register. Okay? When you're done with that, it'll always have 3 zeros on the right side. So you can always add some value to the resulting value that you put in the whatever you use for the RD register in order to set those other 3 digits, okay? Now, there's a little goofiness going on here, and that's what this narrative down here discusses. So let's look very closely, because this is thematic, all right? If you look at these particular pseudo instructions, they've been adding more as the specification evolves, but these are the LA right now and the LI are the ones that we need to focus on right now. Now, I've updated my description on how the LI instruction works. The LA up here is still written the way their document used to describe it, which is, I would argue, mildly incomplete. It's still sort of right. But look what's happening here. We got an AUI PC followed by an add immediate, all right? And the symbol represents the value of this second parameter over here. And by calling it symbol, these are assembler symbols or labels, right? Or C program variable names that become symbols in the link editor. And we're going to see more about that as we move on here. Okay, so what's going on here? This is either AUI PC followed by an add immediate. And remember, AUI PC is a lot like LUI in that it says take this value over here, this parameter, this argument here, and add it to the left half, in this case the program counter, and put that sum into the RD register. So it still has like 3 zeros after it, sort of. And if you wanted to add a 32-bit value to the program counter, you have to do it in these pairs. Now, this is a little more complicated with the program counter and the blah, 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 blah. That is a superset, in other words, of LUI. Okay? LUI and AUI PC accomplish the exact same thing if the program counter is 0. Okay? If the program counter is not 0, the difference is sort of like you got a LUI plus the program counter plus this value over here. All right. So without the program counter involved, this is one step easier to understand. So let's look closely at what's going on here. LI, some register in some 32-bit number. Well, we know that if I wanted to put the most significant 5 hex digits of this number into this RD register, what I need to do is shift it right 12 bits. Okay? Then I can add this other stuff to set the least significant 3 digits. Well, I'll work one of these out by hand. You can see closer, all right, in a second. But look what happens over here. I'm going to add an extra 1 to the value here after it has been shifted. If one of these bits is set in this number, the argument over here, okay? Well, what bit is this? This 800 thingy here. It's the most significant bit of this digit here. Well, it turns out that is the most significant bit of the number after I take the lower 3 digits out of it, okay? So what I'm really saying is, look, if the add immediate instruction that's going to follow the LUI is going to add this value, and it turns out to look as if it's a negative value after this is done, I need to first add an extra 1 to the argument in the Louis instruction. Now, to understand that a little bit better, let's first look at this example before we work it out in detail. All right, so what do I say? It includes this conditional addition to 1. Well, that's this thing that's going on over here, right? This is a conditional expression, a ternary operator. And it's because the immediate operation in the add I is sign extended. Remember, whatever you put here is going to be sign extended, and that's the whole point. All right, so if the immediate operation, the add I, looks like a negative number, then what will happen is the sign extension, like if I wanted to work this particular example out right here, if I wanted to store this 1, 2, 3, 4, 5, 8, 0, 0 into register X5, and I'm naively just simply said, okay, there's the 1, 2, 3, 4, 5, and I'll add this 800 on here, I'm not going to get the right answer because once I extend the 800, I really am adding that value there. And if I say 1, 2, 3, 4, 5, 0, 0, 0 plus this, I'm going to get that value there. Now, if that's not yet obvious and you can't do it in your head, let's take a detailed look at what's going on. Louis, register 5 with hex 1, 2, 3, 4, 5, and then do an add immediate X5 plus hex 800, store the result in X5. So what do we get if we're going to do this? All right, well, first of all, we know that if we Louis register 5 with these 5 hex digits, we're really going to end up saying X5 equals, here's the 5 hex digits we want to load. It's going to create a 3 digits on the right side and store that in register 5. That's what the Louis instruction does. Add immediate treats this as a signed value. All right, and the fact that 800 in hex has the most significant bit set, that's a negative number. So this is where things go a bit awry here. So let's see what happens if we add 1, 2, 3, 4, 5, 0, 0, 0 plus hex 800. Before it does the addition, it's going to sign extend this value, and that's going to mean we're really adding this. Okay, hopefully that's readable. I wrote it a little bit small even for myself. Sorry about that. Then we're going to add all this together. So 0 plus 0 is 0, 0, 0 is 0, 0 plus 8 is 8. Because these are 3 zeros over here, okay, we will never have any carries in these 3 digits, okay, here. There will never be a carry that comes out of this place value, all right? That's the key here. Now, if I add 5 plus F, what do I get? We end up with 4 and a carry, okay? What do we get if we do this? Well, 4 plus 1 is 5, plus F is 4 with a carry. 3 plus 1 is 4, plus F is 3 with a carry. 2 plus 1 is 3, plus F is 2 with a carry. 1 plus 1 is 2, plus F is 1 with a carry, all right? Now, this carry is thrown away, and this is our result, okay? Now, it should make some sense that in this particular position right here, in this case, if we add 1 somehow to this position right here, we would have gotten the right answer, right? Which would have been 1, 2, 3, 4, 5, 800. That's what we're looking for, right? That's why I wrote all this in red, because this will give us the wrong answer. So let's do it again. And look what happens if we increment this value by 1 when we have a negative value here, right? All right, so let's see what happens when we do it this way. We added an extra, we incremented this by 1 because the sign bit here is on. Any value in here that's 8, 9, A, B, C, D, E, or F will have the most significant bit set, all right? So what do we end up with here? We say X5 will be set to 1, 2, 3, 4, 6, 0, 0, 0 in hex, right? And comment there. And we're going to add this sign extended version of hex 800 to this in the add instruction. So what do we get? We get 1, 2, 3, 4, 6, 0, 0, 0. We have our 800 here. We sign extend that one. What do we get? 0 plus 0, 0, 0 plus 0, 0, 0 plus 8 is 8, 6 plus f is 5 with a carry, 4 plus 1 is 5 is 4 with a carry, that's 3 with a carry, 2 with a carry, 1 with a carry that's discarded, and now we have the value that we've been looking for. So if and only if we have a sign extended value, a negative number here, we have to increment this guy here by 1 somewhere, somehow. And in the pseudo instruction, what we do is we just increment this place right here by 1 so that this all comes out all right. Just for fun, let's look and see what happens if we were to add, I don't know, 700 to this thing, right? Well, if this one added 0 hex 700 or 7ff or something like that, which is not a negative value on its own, right? Therefore, when this is sign extended, we will end up with a 700 here, and 1, 2, 3, 4, 5 zeros over there. 1, 2, 3, 4, 6, 0, 0, 0. If you add these two together, you'll get 0 plus 0 and 7 and 6, 4, 3, 2, 1. So if you, in other words, wanted to load a X5 with 1, 2, 3, 4, 5, 700, you would not want to add that extra 1 to this value here, which is this digit there, as you know, okay? Because you'll end up with the wrong value. It's when the immediate value is negative, when you treat it as a signed value, that this sign extension will affect, realize that this number here on its own is -1. Right? So it should make some sense that if you have some number up here, it's going to subtract 1 from this part alone. And this is only true, remember, because there's no carries that can ever come out of this part of the box, because you're always adding values to 0. It's impossible to get a carry when you have 0 plus something. All right? You'll never end up with a carry coming out of that in either case, right? So that's why we do this extra 1 thing here. Now, I strongly suggest you give this an extra read, work some of these out by hand to confirm, to convince yourself that this is in fact true. All right? You also want to take a closer look at what happens when you're trying to use the LA instruction. Let's look more closely at how that one works and what happens with the symbol and the extra 1 that is involved in there. Okay? Let's work some of these out by hand. All right, so the essence of the LI instruction was to tell the assembler to just figure out how to get that 32-bit number in there and just do the right thing for me. And what we need to realize is it's going to generate an extra instruction in there when we look at what happens as a result of our code, right? Now, the same thing is going to happen if you use the LA pseudo instruction. Now, what this does is it's going to result in creating an AOE PC followed by an add immediate. All right, now among other things, it's going to have this problem because that's what add immediate does. So again, let's say we're storing the result in X5. If this value here has its most significant bit set, then whatever we get from AOE PC over here will have 1 subtracted from the leftmost 5 digits, just like you saw with the LI, okay? So what is the point of LA? All right, now the LA really is, let's say X5, because that's what maps to this over here. And I want to put a symbol here. Where you use this is, let's say I got some code here. I'm writing, some operation here. And I want to do something like, I want to load, maybe I got a symbol over here like, variable 1. And, maybe you've got some a word in the GNU assembler, you say word, and you give it maybe a 0x 1 2 3 4 5 6 7 8. Why am I dotting my ones? I don't know. Here's a 32-bit word, and let's say I want to know the address where this word is stored. I can say LAX5, in this case var1, right here. X5 var1. And what I'm telling the assembler to do is say, look, just figure out how to get this stupid address from over here on this symbol into X5, because there's no single instruction that can do it, all right? And it's going to do it like this. it's going to take the address of the LA. So let's say that this is the beginning of a program, and this is at address 0, that's at 4, this is at 8, because every instruction is 4 bytes long when we're dealing with RV32I, okay? Let's say there's some more instructions in here, and maybe this is at address 100 in hex, okay? So in order to get the address of R1 into X5, it needs to get this 100 in here. What it wants to do is it's going to take the program counter at address 8. Okay, and it's going to say what's 100 minus 8, and that would be F8. Okay, right? So the distance in here is going to be F8, right, in hex between 100 and 8. And it's going to add that to the current program counter in order to come up with the address where this is located, okay? Now, the reason it does this in this weird way is because the distance can get really big here, okay? It could be as big as, 4 gigabytes away, in which case it would come all the way around, but it could be almost 4 gigabytes way at the end of memory, all right? So it needs to account for all possible scenarios. So in this particular case, what it wants to do is it wants to add 0x 1, 2, 3, 4, 5, 6, 7, 8 digits in hex to the current program counter, which is 8. All right. So what's it going to do up here? Well, it's going to first shift this right 12 bits, which effectively throws these away, leaving this value here. So it's going to say LAPC X5 0. Okay. Then it wants to add this F8 because that's the other part of this. This goes in here. 0F8. Now, this is fine. Why? Because this is a positive value, and everything's going to work out just ducky. It'll be F8 plus the program counter where this instruction is, and it'll come out to 100. Let's say this is not at 100 in hex, but at E00 in hex. All right, now we have a problem. Okay, if we want to add E00 minus 8, that would be what? DF8. So we would change this. Let's not just hack this up. Let's just say like this. It was 0x 1, 2, 3, 4, 5. And then this would be DF8 plus 8 would give us the E00. All right, so that's nice because these are still zeros here. So this instruction is still really just stick 0 into address X5 and adds the program counter, which actually ends up putting 8 in X5. I'm sorry, I misspoke right there, right? And then we have to add the DF8 here. Well, this is no longer that, but DF8. Well, now, and we have this sign extension problem again, right? So LEPC X50 is going to put 8 into X5. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, because it's the program counter plus 0. Then we want to add DF8 to this thing. Well, we got to be careful because remember, add immediate is going to add DF8. If we code it this way, we add this up, we get 0 with a carry. That's going to be 0 with a carry. There's my nice E00. However, I don't have a carry out of here, so I'm going to end up with F. This is not what I want, okay? So we go back to the same scheme we did with load immediate. If this sign bit is set, when we do the add, we add 1 to the operand over here. So rather than adding 0, we will add 1 in that scenario. Okay? Now, we end up with what? If you LEPC X5 1, it's not 9, it's 1, 2, 3, 4, 5. This is the left half, right? The upper part. 000 plus the program counter, which is 8 with all zeros over here. Right? Plus now the DF8. So first thing we're going to end up with is 1, 2, 3, 4, the 1, and then we're going to have 008, and then we're going to have DF8 here, and then it's going to get sign extended like this. And you can see that 1 and how it's going to fix out everything. 8 plus 8 is 0 with a carry, 0 with a carry. There's my E 0, 0. F plus 1 is 0 with a carry, 0 with a carry, 0 with a carry, 0 with a carry, 0 with a carry. That gets thrown away, and now we have the right number. Again, this is the same exact thing. If you have this pair of instructions, and you're using the add immediate to adjust these least significant 3 digits over here, you have to be careful if this thing has a bunch of F's when it gets sign extended. So you have to add 1 to this argument here of the OWI PC. All right. So now we have a good understanding of what LA and LI does and this weirdness going on. We don't have to worry about this when we write the assembler, which is great because it's otherwise a big pain in the butt. If LA and LI are our friends, okay? Thanks for watching. See you next time.